So hi all, so my name is Jennifer Sowen and I'm a first year chemistry graduate student at UC Berkeley. And so I made a video to share with you all as part of the Be a Scientist program, which is now virtual due to schools being canceled. But I'm going to be sharing with you today how I came to pursuing a career in chemistry, as well as how I began to develop interests in chemistry research. So a brief summary is I make and study gold complexes. And so I find these gold complexes interesting because they undergo interesting reactions with visible light. And then some of the reactions that these gold complexes can promote can be used to make complex molecules such as drugs. And then in addition, some of these gold complexes have biological applications. So some of these gold complexes are anti-tumor drugs. And so here are two examples of me, science in action. So this is me presenting my poster at a poster session during my second year of college. And then here's a picture of me with my lab partner in my inorganic chemistry lab during the second year of college. And we're pointing at the vials of the metal complexes we made over the course of the semester. So my path to chemistry began in Appleton, Wisconsin, which is a town in northeast Wisconsin. It's located along the Fox River, and it was a very nice place to grow up, although had very cold winters, much colder than here in Berkeley and California. And then in 2015, I decided I wanted to become a Wisconsin Badger, so I moved to Madison, Wisconsin, where I began my undergraduate studies at the University of Wisconsin-Madison. And so it was at the University of Wisconsin-Madison that I began to develop my passion for chemistry that I have. And this was because I like to be able to investigate interesting and important problems in the world around us. And then there was the added perk that my complexes I was studying metal complexes and the reactions they promote. And many of these metal complexes were brightly colored, so I got to see lots of different colors every day when I would do my chemistry research. And then in fall 2019, I decided I wanted to become a Cal Bear and moved to California, so I started my PhD in chemistry at UC Berkeley in fall 2019. And so I have other interests outside of chemistry, so I like to run. I ran competitively in high school, but after that I just run for fun, and I like the views that I get to see, especially in California on my runs here. I also enjoy hanging out with friends and family. This is a picture of me with some of my friends from one of my research experiences when I spent a summer at Harvard. I like to also hang out. This is my mom's cat, which likes to sleep in funny positions. I also like trying new food. So this is me getting boba tea in Berkeley, which I quite enjoy. I like hiking. I like puzzles. I did this puzzle of the Golden Gate Bridge over winter break. And then one of my favorite things that I got to do in Madison was Madison is an isthmus located between two lakes. And so I would go in the summer to an outdoor seating area on one of the lakes, and I would get to see the pretty sunsets for a lot of the nights during the summer. So I began becoming interested in studying metal complexes during my second year of studies at University of Wisconsin-Madison. So I made these different metal complexes during that inorganic chemistry lab that I showed you the picture on the first slide. And so you can see they're basically every different color of the rainbow that they are. I also made, this is one of the complexes I made, this is called Prussian blue, and it's this iron complex here with this general structure, and it's this lovely dark blue. And then I also made this cobalt complex, and this is the structure corresponding to the complex I made, although I don't have a picture, unfortunately. It was also a pretty deep blue. So then the question that I want to talk to you about today is, why are these metal complexes these bright and pretty colors? And so the short answer is that the wavelength of light that the metal complex transmits is what we're going to see, and that's going to be the color that we see. So this scheme here I'll use to try to explain how we see different metal complexes. So here this would be the metal with some things bound to it. So M is representing the metal and L is what we call a ligand, is what's bound to the metal. And so say you have a solution of some metal complex, then, and some light source is coming in, say the sun, some like a beam of light comes in and hits your metal complex. Some amount of that light will be absorbed by the solution and some amount will go through the solution. And so what you will see will be the transmitted light. And since your eyes can only see the visible part of the spectrum, you will only see that part. So here, this complex you were seeing is red. But how do we rationalize what color we're going to see based if we know what color it absorbs? And so that can be explained using this color wheel here. You've probably encountered color wheels in art classes with complementary colors, but generally the color that a complex transmit will be opposite on the color wheel to what it absorbs. So this complex here is absorbing green, so then you're seeing red. Another example would be, say a complex was absorbing blue, then you would expect that that complex would appear orange to your eyes. And then, so here is an equation, so the energy that the complex is absorbing and transmitting is related to the frequency of the and wavelength of the lights that you're absorbing and transmitting. And so the wavelength is related to the color you're seeing. But this energy can be different for different metal complexes based on the structure. So you would expect that different complexes could absorb different energies of light and transmit different energies of lights, and they would be different colors with different structures. So then what are some of the factors that make metal complexes different colors? So one of the answers is, well, it depends somewhat on the metal and what charge it has. So this scheme here, you could see the chromium complex. These have different charges. So there's the 2+ chromium complex, which is blue. One with a 3+ charge is green, and one with a 6+ charge is orange. But then also between different metals, these can also be different colors. So these are all 2+ charge. The cobalt complex is red, the nickel complex is green, and the copper complex is 2. But then it also can depend on what is bound to the metal. So the ligand, which I introduced in the first slide. So these are cobalt complexes with different ligands bound to them, and they're all different colors because this changes the energy that the complex absorbs and transmits. And so I've listed the different things that are bound to the metal. Some of these you may have never seen, but I want to point out that some of them you probably have encountered. So ammonia, you've probably seen in household cleaners, you've encountered water, and potentially cyanide is something you might recognize as you've heard is pretty toxic. And then, so in addition to being really pretty, colored metal complexes they have a lot of applications in the world around us. So this is an example, that dark blue powder I showed you in one of my earlier slides, this Prussian blue, the iron complex. And its application in the real world is that they use it for the color for blueprints, for designs of things that people make. So then that kind of leads to my next slide, which is the challenge questions, which could you think of other places where colored metal complexes appear in your everyday lives? So what might be helpful to start thinking about this is think about the blueprint example and the color being used in that. Are there other ways that the color could be used in your everyday life? But there are other examples as well. Do you think a metal complex could be a different color in different solutions, and why might that be? And then this is one of my favorite examples from inorganic chemistry. So when I heated metal complex to dry at once, it changed color. Why do you think the color change might have happened as I heated the complex? What might have been happening? And then what might make a metal complex appear colorless to my eye? What do you think might be the reason for this? So I'm gonna end this video with you thinking about these challenge questions, and then I'm excited to be able to meet you during the lab section to discuss what you think and then any other questions you might have.